So Chapter 6, Exponential and Logarithmic Functions continued, and Section 6.6 is solving logarithmic and exponential equations. So the first objective is solve logarithmic equations. And the second objective is to solve exponential equations. And we did some simple ones today, but these are going to get a little bit more complex. So just some things to remember. Y equals log base A of x if and only if a to the y equals x. So remember that logarithmic form is the y equals log base A of x. And exponential form is the a to the y equals x. And remember, we want positive a, but a not equal to 1. So recall that the log of a product equals the sum of logs, so we need to be able to use this idea. And for solving logarithmic equations, you're actually going to use it backwards. You're going to be combining into a single log. And then remember that the log of a quotient becomes the difference of logs. And that the log base A of m to the r is r times the log base A of m. And that a to the r equals e to the r ln a. So let's get on to objective 1, solving logarithmic equations. So if you can, you want to manipulate your equation using properties of logs until you have one logarithm on each side. With no coefficients. So you don't want 2 log base 7 of x. You want to put this 2 up as a power so that you have no coefficients on the logarithms. And then you can use this property that says if you have 2 logs that match, then the arguments have to be equal. So I'll have log base 2 of x cubed equals log base 2 of 27 to the negative 1. Well, then that says x cubed must equal 27 to the negative 1. Well, that says x cubed equals 1 over 27. So x must equal the cube root of 1/27, which is 1/3. So we've solved this logarithmic equation. Another way to do it would be to add the log base 2 of 27 to both sides and have that it's equal to 0. Then you could bring this 3 up and say log base 2 of x cubed plus log base 2 of 27 equals 0. Then you could use properties of logarithms and say, well, that's the log of 27x cubed that has to equal 0. Well, now I write it in exponential form as 2 to the 0 equals 27x cubed. Well, 2 to the 0 is 1, so 1 over 27 equals x cubed. So get the same answer either way. It's just another way of doing the problem. Okay, so number 14 we'll do in class together. So in solving logarithmic equations, you'll want to combine all the logarithms into a single logarithm using properties of logs, and then write the equation in exponential form and solve. So 2 steps: combine all the logs into one log, write in exponential form, and then usually you'll see how to solve it after that. So solving logarithmic equations, it says express irrational solutions in exact form first, and then as a decimal rounded to 3 decimal places. So here I'm going to combine my logs into a single log using the property of logs that says if I have a difference of logs, that can be written as the log of the quotient of the arguments, and that equals 1. Well, now I can see that there's no base written, so that means it's base 10. So now I write it in exponential form. 10 to the 1 equals 2x over x minus 3. And if you ever have a variable in the denominator, you're going to want to multiply both sides by that denominator because that's the only way to get the x that you're after out of the denominator. So then I'm going to have 10x minus 30 equals 2x. So 8x must equal 30, and x must equal 15/4. And then you must check your answer. So you at least need to plug it in and say, well, if I have the log of 2 times 15/4 minus the log of 15/4 minus 3, this is greater than 0, so we're okay. This is greater than 0, so we're okay. Because remember that the domain of log has to be positive. Okay, so let's look at number 24. You're going to add the log base 5 of x minus 1 to both sides. So then you're going to have log base 5 of x plus 3 plus log base 5 of x minus 1, and that's going to equal 1. So I use my property of logs to say, well, this is the log base 5 of x plus 3 times x minus 1, and that has to equal 1. So now I write in exponential form, 5 to the 1 equals x plus 3 times x minus 1, and I'm betting you can solve this. But let's go ahead and work on it together. I'm going to move it down here and say that 5 equals x squared plus 2x minus 3, so x squared plus 2x minus 8 equals 0. So that looks like x plus 4, x minus 2. Check me on that. So x equals negative 4 or x equals 2, but then you have to check in the original equation. So you're going to say log base 5, check x equals negative 4. Log base 5 of negative 4 plus 3 can't take log of negative number. So that's not a solution. So how about x equals 2? Log base 5 of 2 plus 3. And we want to know, does that equal 1 minus the log base 5 of 2 minus 1? Well, this says log base 5 of 5 equals 1 minus, and then remember the log of 1 is 0. So x equals 2 is our only solution. And let's do these next two together in class and go on to solving exponential equations. So if we can write both sides with the same base, we've already done problems like that where then we can just equate the exponents. But if the problem isn't that simple, we need to use logarithms to solve. The first step must always be to isolate the exponential function. I can guarantee you grief if you don't do that first. So let's look at number 48. To isolate the exponential function, I need to divide both sides by 0.3. So 4 to the 0.2x equals 2/3. So now I have the exponential function isolated. So I'm going to use ln. ln of 4 to the 0.2x equals the ln of 2/3. And it doesn't matter, but with the ln I'll be able to find the decimal approximation. So then we use the property that says the power can come down in the front. Remembering that ln 4 is just a number. So I'm trying to solve for x. So I need to divide by 0.2 times the ln of 4. So my exact answer is x equals the ln of 2/3. Remember we did this today of if we're dividing by 2/10, it's really the same thing as multiplying by 5. And then we're over the ln of 4. So then we could get our decimal approximation. So this is our exact answer. An exact answer is always wanted unless a decimal approximation is asked for. Okay, so let's do number 50 in class together. And then this is the last type of exponential equation we're going to look at. And this is quadratic in form. So remember that quadratic in form means A, something that looks like an x squared, plus B, something that looks like a x plus c equals 0. But remember, we looked at ones that look like w to the 4th plus 6w squared minus 7 equals 0. So if the pattern held true, then we could use the quadratic skills that we already have to solve the equation. So notice that if I say w equals 3 to the x, then w squared equals 3 to the x squared, which is 3 to the 2x. So do you see that we can rewrite this as w squared plus w minus 2 equals 0. So we know how to solve this. We factor, and we only have choices of a 2 and a 1. So the 2 must be positive and the 1 must be negative. And then we use our zero product property and say w plus 2 equals 0 or w minus 1 equals 0. So w equals negative 2 or w equals 1. Well, w is 3 to the x. So can 3 to the x ever equal negative 2? There's no solution to this. There is no way to solve it. And if you think about taking logarithms of both sides, you'll see why, because you can't take the logarithm of negative 2. And if you just think about how an exponential graph looks, that's why we take time to think and talk about the domains and ranges, so that you can say there are no negative numbers in the range of an exponential function. So it's not possible to get negative 2 as a result. Okay, so then w equals 1 would be 3 to the x equals 1. Well, you can make this complicated by taking logs of both sides, or you can think about it and say, well, if I have 3 to some power and it equals 1, then the power has to equal 0. So x has to equal 0 is going to be the only solution. So if x is 0, does that work? Yep, 3 to the 0 is 1, plus 3 to the 0 is 1, minus 2 equals 0. So x equals 0 is the only solution to this equation. Okay, and then we'll look at number 60 and 67 in class. They're a little trickier. Okay, so then here's a problem that I want to look at together and think about the meanings of this question, but you have a homework problem like this, so I wanted to make sure and talk about it with you. So that's it for this section.